So I didn't write down the full question, but basically this is a company buys like thousands of wine bottles and with the company logo on it. It's 25 ounce. They asked for that exact thing, and there was a vendor that supplied the wines, and they got it, right? But then when they drank a few of them, they realized, hey, this seems to be a bit under. So they're interested to see if they can actually sue the vendor and get some money back. Right? Because companies do that all the time, right? Okay, so how do they figure this out? Well, they take 10 wine bottles, measure the amount of wine in the wine bottles carefully, and obtain the fact that average was 24.3. Definitely less than 25, but you know, maybe your 10 bottles that you sampled were just by chance a little lower than the average. Who knows, right? So you can't be sure, but you also found out that the standard deviation is 0.9 ounce. And it says use 0.05 significance level to conclude whether average wine amount is 25 ounce. Now, we were talking about confidence intervals, confidence level, and here is significance level. Significance level is what we call as alpha, okay? Also known as alpha level. And so they add up to 1. Okay? We use confidence level for confidence interval because when we present a confidence interval, we're saying we are 95% sure that this confidence interval is going to capture the entire average. Okay? And that's why we use confidence level whenever you talk about confidence intervals. On the other hand, when you're trying to argue something is not right, when you want to do the hypothesis testing, you have to say that the data presented fits into that 5% or maybe 1%, whatever significance level that you think is appropriate, or the question is giving it to you. You're using the fact that the data set presented can only happen with this much probability or less. Okay? That's why we use significance level, because if it's a very small significance level, then there's a very low probability that that could have happened just by chance. So you can argue that, oh, we can't trust the original assumption that it's 25. So that's the reasoning that we're trying to go about. Now, whenever you try to argue using statistics, you first need to establish a hypothesis. And there is something called the null hypothesis, and H0 is called the null hypothesis, and this one is called the alternate hypothesis. And null hypothesis is like the status quo, and it's the basic assumption you carry out all the statistical calculation with. Okay, you always use the basic assumption in the null hypothesis to carry out the calculations, and if the calculation seems to be very improbable, less than this 0.05% chance, 0.05 probability chance, then we can reject the null and say H1 is right. Okay, that's the way that we're going about this. So what's our null hypothesis here? It is that
mu equals 25.
Mu equals to 25. Thank you. That the average of the entire thing is 25. And then what is the here it says that conclude whether average wine amount is less than 25 ounce. And if you want to show that something's less, then the alternate hypothesis is doing something like this. You're saying that, oh, it's less. Here's 0.05, and our data fits right here. Okay? So this is a one-tailed test, and the alternate hypothesis is saying that no, mu is less than 25. That's what you want to show. Okay? Okay. Now, question. Should we use the t-test or the normal distribution?
T.
T. We have to use t. Why?
Give the sample standard deviation.
Because we have sample standard deviation. We don't have the sigma, we have S. Okay? In most cases, that's the case. Okay? Now, if the sample size was something like 40, then I don't care which one you use. Okay? You could use normal, or you could use the T. They'll be all about the same. Okay? But see, this is less than 30, and there's even more uncertainty here, so we have to use the t distribution. Okay? So therefore, I'm going to talk about the t distribution, but before that, see, one of the worries that people have is this 0.05 is somewhat arbitrary, right? And people who make these arguments might fine-tune this, and they might look at the data and say, hey, that's like really improbable. I think we can manage to argue even if this is like 0.01 significance. Or they might look at the data and say, it'll be hard to prove that. Let's make this 0.10 significance. It's like you can kind of see the data and tweak this, which is a bit frowned upon. When you do science or engineering, when you choose a significance level, you should be choosing the significance level before you actually do the experiment. So we just have to agree on a certain significance level. And by the way, a lot of times this depends on the field and the context. So in biology, there's so many different things that can happen, so you might have a higher significance level. In physics, they use very accurate instruments to measure things, so they might want a stronger significance level, which is like 0.001 or something like that. Okay? So you want to choose the significance level before you calculate with this. So step one, you have to first choose the hypothesis, and step two, you have to find the rejection rate. You shouldn't calculate the t statistic before you put the rejection region. You have to put the rejection region first. Okay? All right, so our rejection region is a left tail at 0.05, right? What's our degrees of freedom?
24. Or 9.
9, right? Yeah, 10 minus 1 equals to 9. So we go to 9 and look at one tail that's, let's see. I wonder if you can read this. Which one should we be using?
0.10.
0.10, yes. No, this one. 0.05, this one.
Yeah.
So I should be using 1.833. So that tells us that our T alpha is 1.833. So Notice that I didn't put over 2 here because it's a one-tail test. If you have 2 tails, you have to split this into 2. Here, you don't have to do that. Okay? And this is like, for some reason in our table, this has the value of t of 0.95. Now, what's confusing is that this doesn't mean that alpha is 0.95. It's customary to just put alpha here as a decorator to say that this is a one-tail test. Okay? When you see t alpha over 2, that just means it's a two-tail test. Okay? And when you see t 0.95, what this means is that if you start from negative infinity and end at 1.833, this captures 0.95 of the entire probability. This is 0.95. So what this means is that if you go from negative infinity until negative 1.833, what would this area be?
0.05.
0.05, right? So that's going to be our rejection region. So step 2, our rejection region would be that the t statistic is less than negative 1.833. Notice that I went from the positive to negative because we're doing the left tail. If it was conclude whether average wine amount is more than 25 ounce, if that was the case, then it would be the right tail. Okay? Any questions? Okay. So we got the rejection region. And now step 3 is when you calculate the t statistics. So t statistics is obtained by, see, our mu is 25, right? And what we got from the sample is 24.3. So what we do is we take 24.3, subtract the purported 25, and we divide it by the possible standard deviation of this one, which is 0.9 divided by square root of 10. Okay. So that's what we have to compute. Can somebody compute this for me? It's important that you put a parenthesis over here, okay? And parenthesis here. The number one mistake people make when calculating this is forgetting to put these parentheses. It's not in the formula, that's why. In the formula sheet, I don't have these parentheses. You have to put them in. Okay. What do you get? Well, I have it here. Yeah. What do I have? Oh, negative 2.45. Yeah, negative 2.45. Okay. And then step 4, what happens is that in step 4, does this belong in the rejection region?
Yes.
Yes, right? What does that mean?
That their claim was like wrong.
The claim of 25 ounce is clearly wrong. They were like, somebody in that plant was taking some wine home and drinking them in their private time. And that's what happened. So now the company can gather this data and present it. Well, they might settle out of the court or something, but they're going to get some money back. Okay? So that's what statistics is good for. It saves you money, and sometimes you can win court cases. All right. So step 4 is now you can conclude. You can conclude that since t equals to negative 2.45 falls in the rejection region, RR, rejection region, okay? We reject the null hypothesis, okay? And accept H1, meaning that the average amount of y is less than 25 ounce. Okay? So that's your conclusion. It's pretty neat, right? Yeah. But on the other hand, people who are used to math and physics might not like this so much. Well, maybe for physicists it's okay, but if someone who's always used to getting correct answers, 100% true in math, looks at this, feels a bit uncomfortable with the fact that you could be wrong. This conclusion could be wrong what percent of the time? 5% of the time, because we're using 5%. If you repeat such tests for variety of similar situations and you either reject H0 or fail to reject H0, you would be still wrong 5% of the time. Actually, 5%, not actually 5%. This would be the probability that there is 5% probability that when H0 is rejected, H0 still could be right. Could have been right. Okay. There's 5% probability. So if you're, again, the manufacturer or the vendor, you might try to argue with this 5% or make some big deal about it. And hope that the jury could be on your side or something. Okay, some other items. We never accept H0. That's another thing. When you do hypothesis testing, we only fail to reject the H0. When, let's say, we calculated a t statistic, it was still low, but it came out to be, say, t equals to -1. What happens? Well, it is low, but it's not in the rejection region. What do you say? Well, we say we failed to reject H0. Okay? We never say, oh, this proves that H0 is right. That never happens, okay? Yeah. You can't really prove something is right. Well, I guess you can say with 95% confidence level, the average should be in some interval. That's all you can say. You can't say H0, like H0 where you say average is exactly 25. That would be very hard to do, right? Okay, so that's one thing. You never accept H0. You either reject H0 or fail to reject. There are only two possible outcomes of a hypothesis testing. Okay. Second thing is, because there are possibility of wrong conclusions, there are types of errors in a hypothesis testing. So, let me call that. Types of error in hypothesis testing. There is a type 1 error, and there's type 2 error. Type 1 error is when you reject the null but H0 was indeed correct. Okay. Type 2 error is when you fail to reject H0, but H0 was wrong. Okay. In the wine bottle story, type 1 error would be we just rejected it, right? But later on, the wine company came in and inspected all the wine bottles, and then they found a batch that had a lot more wine, and then it turned out that the average was indeed around 25, not like less. Okay, so that could be type 1. Type 2 is sometimes you don't get a significant t statistic to come up with the correct conclusion to reject H0, so you fail to reject, but despite that, it's still wrong. Okay? Do you know the story of Boy Who Cried Wolf? Right. So in the Boy Who Cried Wolf, what's like the null hypothesis? Well, status quo, it's like no wolf, right? Yeah. Right? No wolf will be normal life. Okay? That's your H0, status quo. And then initially, what does the boy say?
That there is a wolf.
There is a wolf, right? You rejected the null hypothesis. There's no peace, right? And the villagers came in, and what did they find?
There wasn't one.
There was no wolf, right? And he did that, what, 3 times, right? Later on, nobody believed him. So what happens at the end of the story?
He says that there's a wolf, but they don't come and help him.
Yeah, because the villagers make the type 2 error, right? Villagers think that it's still peacetime, right? But it turns out that there was a wolf devouring all the sheep. Okay? So if you just picture this Boy Who Cried the Wolf, you can kind of distinguish what's the type 1 error and the type 2 error.